In the next few slides, we'll use the Z transform approach to solve this difference equation with the input un and cosine 0.1 pi n. And I guess this is a revision because we already have done this in the past, but let's proceed anyway to see how we can get the Z transform to generate our output. Let's start with our difference equation. This is our difference equation, and when we use the Z transform, this is our difference equation in the Z domain. And of course, we are interested to get the y's on one side and the x on one side so that we can get this numerator of yz divided by xz to get the transfer function. And when we use this manipulation, we get 1 over 1 minus 0.5 z to the power minus 1. Remember, we do not like to operate on negative power of z in partial fraction, so we multiply top and bottom by z to get this well-known form. So now what we need to do is that we have the transfer function h of z, and remember what we need to do is we need to say y of z is equals to x of z times h of z. So we already have solved this guy. So what we need is to get x of z. X of z comes from x of n, and we have two parts of x of n, u of n and 0.1 cosine 0.1 pi n. So we have two terms here, and we need to do the Z transform of these two terms. The Z transform of u of n is this, and the Z transform of cosine 0.1 pi n is this. This is by lookup table, and then because the system is linear, we can study them individually. Well, never mind. Let's just plug in x of z here first. So this is unit step, and this is the cosine 0.1 pi n. This of course is h of z, and we are going to just multiply. But if you try to do this, it's going to be very messy. So instead, we are going to study them individually. Alright, but before that, there's a tip. Please move one of the z, and typically we get the hz as a z on top. We move it onto the left hand side, and your hz becomes hz divided by z. And the reason is that later on this z will move to the right hand side to find the inverse z transform. That's all. Okay, so let's go and try to manipulate. The first thing we want to do is to use the unit step. So this is our hz divided by z, this is yz divided by z, and this is a z transform of the unit step, and we will ignore the cosine 0.1 pi first. Okay, so we just study one term or one of the terms of the input. And now this is nothing but partial fraction expansions, so you keep on manipulating the equations to get into this form, and then you have to do partial fraction from here to here. Of course, I use MATLAB to check. So what you need to do is, once you have it in a numerator divided by denominator, you can use the MATLAB's residual function and plug in the coefficients of the numerator. So it's 0, 1, 0, 1 minus 1.50. So basically, we are using the coefficients of the power of positive z's and plug it in. RPK will basically give you R and P as well as K, and then you plug in this equation in the partial fraction expansion form. So 2 comes to here, 2 is the top numerator, and the corresponding pole is z minus 1. Minus 1 goes to here, and the corresponding pole is z minus 0.5. And K is 0, so this is plus 0. K equals to 0. Alright, so now what we're almost in the form that we can have lookup tables, right? So this is the form of the partial fraction, and now this z moves back to the right hand side, so all the z comes back, and this has lookup tables. So 2z divided by z minus 1 is 2 unit step, so 2 goes out, z over z minus 1 is unit step. Z over z minus 0.5 is your exponential. This pole becomes here, and this is un. So this is the steady state response because this lasts forever, right? Un lasts forever, 2, and then it will remain as 2. But this guy although it's causal, this guy dies now. So this is a transient. So 2un minus 0.5 n and this is our yn. So where did we see this equation? We see this equation exactly here. 2un minus 0.5 n un. 0.5 to the power of n, and then it is for only positive index n, because we are doing the loop for n equals to 0 to n minus 1. So this equation, YZ transform, actually came from that slide that we have just completed. Now we are going to use Z transform to solve for 0.1 pi n input. So this is slide page 10, and in this slide we're going to do the same again. We have YZ over Z, and we have HZ over Z here. And basically, this is the Z transform of the cosine 0.1 pi un. So this is by lookup table. And then now you have a quadratic equation. And now this quadratic equation will multiply with Z to the power of 1. And therefore you have a cubic term below. And you have a square terms on top. Now this is very hard to solve, so I just use again RPK residual to find my poles and my zeros so that I can get into this form. Alright, now it will come out as rectangular numbers. You can convert it into polar numbers for ease of manipulation. And the trick again is this: you have to identify the pole that is sitting on the quadrant 1 or quadrant 2. That means on the positive j's. So this is the positive j's. And the reason is that later on you'll see that it will be a pair of them, and you can use the cosine function to represent these two poles. And this is what I'm talking about. You manipulate such that you realize that you have a quadratic term as the pole, and as well as the numerator. So these are pairs: 0.91 minus 0.28, 0.91 plus 0.28. So this is 1, 0.3. This is 1 minus 0.3. So the values of the numerator and the values of the pole have conjugate terms. Anyway, what you will realize is that when you manipulate, 0.91 drops out here, minus 2.83 drops out here, and because there are two of them, so we have a 2 here, and the pole is sitting at 0.1 pi, so 0.1 pi is 0.314. So you see, so these two terms together form this cosine with this gain and phase shift. And what about the transient? So the transient came from the exponential that is decaying at 0.5 to the power of n. So it's 0.7755 pi. What does this mean? This means, what is 0.755 pi? So it's minus 0.755 is equals to 0.755 angle pi, or angle minus pi, up to you. So a negative number have a phase shift of pi or negative pi. That's what it means. Anyway, so we have reduced our equation by inverse Z transform to the time representation, and we see again the transient response here. So where do we see this equation? This equation is exactly here in line 24. This is the steady state gain. This is the original input. This is the phase shift, and this is the transient 0.755 to the power times 0.5 to the power of n, which is here. Okay, so that's it. We're done with how to use the Z transform to calculate for unit step and the cosine 0.1 pi. Thank you.